Imagine being dropped into what most people would call empty space. At first, it feels like complete nothingness, a quiet, lightless environment where there's no sense of direction, no sound, no objects, not even the faint comfort of a horizon, just the kind of emptiness we imagine when we close our eyes and picture the vacuum between stars. But then, as your eyes adjust to the blackness, something unexpected begins to appear. Small flickers, tiny momentary specks of brightness. Not glowing like stars or sparks, but more like faint pulses that show up for a split second and then disappear again. You notice more of them. They're scattered everywhere. They come and go at random, too fast to track, too short-lived to feel real. These brief flashes are not imagination. They're not dust. They're not debris. They're quantum fluctuations, the spontaneous appearance and disappearance of particles in what we usually call empty space. Even in a region with no air, no radiation, no atoms, no light, something is still happening. Something is always happening. Space isn't sitting still. It's subtly active, constantly shifting, constantly fluctuating. The vacuum, by its very nature, refuses to be truly empty. And this is one of the strangest revelations in modern physics. Even when you take everything away, even when you strip a region of space down to the lowest possible energy allowed by the laws of nature, the result is not zero. There is still motion, still energy, still structure. This is the quantum vacuum, not a clean, silent void, but a restless background field full of temporary, short-lived events that appear and vanish too quickly for us to detect directly, unless we disturb the vacuum in just the right way. If you move through this imaginary scene, you start to notice a subtle texture in the darkness, not a literal texture like bumps or waves, but the sense that the environment isn't perfectly smooth. There's a kind of underlying activity, like static in an old radio, not loud, not bright, but present. And that raises an unsettling question. What does nothing actually mean? For most of human history, we used the word casually. Nothing meant the absence of everything, a blank space, an empty container, a void. But quantum physics has forced us to rethink the entire definition. Nothing turns out to have weight, energy, behavior, rules. In the quantum world, even nothingness participates in the physics of the universe, and it can even exert pressure. This is where the story of the Casimir Effect begins, with the realization that the vacuum, the thing we once assumed was perfectly empty, is not passive. When you change its boundaries, restrict its space, or alter the quantum fields inside it, the vacuum pushes back. Literally, there is an invisible force hidden in that quiet darkness. A force that comes from these tiny fluctuations appearing and disappearing everywhere around you. And later, we'll see how two thin metal plates, placed extremely close together, will experience a measurable attraction. Not because of electricity, not because of magnetism, but because the vacuum between them behaves differently than the vacuum outside. But before we get there, before we watch that surprising, invisible pressure emerge, we need to understand how long it took humanity to question the idea of emptiness at all. The vacuum wasn't always seen as something mysterious. Ancient philosophers debated whether it could exist. Aristotle rejected the idea entirely. Others embraced it. Centuries later, scientists would build the first artificial vacuums, trying to create a space with nothing inside. And then, only in the last century, physics discovered that emptiness was far more complicated than anyone expected. Before we go deeper into that journey, if you enjoy exploring these quieter corners of science, where the universe reveals things that don't quite match our intuition, consider subscribing to Sleepless Knowledge. And feel free to leave a comment telling me where you're listening from and what time it is there. It helps the channel, and it helps these slow, thoughtful explorations continue. Back in our imaginary vacuum, the flickering fluctuations fade into the background again. The darkness looks smooth and silent once more, but now you know what's hiding behind the appearance. Not emptiness, not a void. Something more active, something stranger, and with that, we can begin tracing the long history of this concept, the idea of the vacuum. and how humanity slowly, over thousands of years, went from debating whether nothingness could exist to discovering that nothing is one of the most energetic, dynamic things in the universe. If you go back far enough in time, well before particle accelerators, quantum fields, or even basic scientific instruments, the idea of empty space wasn't just a scientific question. It was a philosophical problem, a deep one, the kind that determined how people thought the universe functioned. The earliest recorded debates about the vacuum came from ancient Greece. Around the 5th century BCE, the philosopher Democritus proposed something radical. He believed that everything in the universe was made of tiny, indivisible units he called atomos, atoms, and that these atoms moved through a background of empty space. To Democritus, the vacuum was not only real, it was essential. Without empty space, nothing could move. No motion, no change, no life. His vision was simple, solid matter floating in a vast backdrop of nothingness. But his ideas were not universally welcomed. Aristotle, perhaps the most influential thinker of the ancient world, strongly disagreed. In the 4th century BCE, he argued that a true vacuum couldn't exist. Nature, he said, abhors a vacuum. His reasoning was intuitive for the time. If you had empty space with absolutely nothing in it, then motion would become impossible to explain. Objects would move infinitely fast, or not at all. The laws of nature would fall apart. So Aristotle concluded that the world must be filled with a continuous medium, something everywhere, even if invisible. This view dominated scientific thought for nearly 1,800 years. It shaped medieval science, Renaissance ideas, and even early engineering. The vacuum wasn't seen as something real, it was seen as a theoretical mistake. If you tried to create one, say by sucking air out of a container, nature would rush in to fill the space. Not because air had pressure in the way we think of it today, but because the universe simply did not allow emptiness. For centuries, the vacuum was an impossibility, but then the world began to change. By the 17th century, Europe entered the scientific revolution. Instruments improved, mathematics advanced, experiments became more controlled, and slowly, Aristotle's authority began to crack. In 1643, an Italian scientist named Evangelista Torricelli, a student of Galileo, performed an experiment that challenged 2,000 years of assumptions. He filled a glass tube with mercury, sealed the top, and flipped it upside down into a basin. Some of the mercury drained out, but a surprising amount stayed in the tube, suspended above the basin as if held up by an invisible hand, above the mercury column. A small empty space. People had seen weird behaviour in barometers before, but Torricelli realised something profound. The column wasn't being held up by nature-resisting emptiness. It was held up by atmospheric pressure, the weight of the air pressing down. For the first time, someone had created what looked like an artificial vacuum, and it didn't break physics. It didn't cause objects to fly infinitely fast. It didn't tear a hole in nature. It just sat there, quietly, as if nothing unusual had happened. This simple setup revolutionized our understanding of the world. Torricelli famously wrote, "We live submerged at the bottom of an ocean of air." In other words, air has weight, pressure, and behavior, something Aristotle never considered. A few years later, Blaise Pascal expanded on Torricelli's discovery. He carried barometers up mountains in the 1640s, proving that air pressure decreases with altitude. At the summit, the mercury dropped lower. As he descended, it rose. This wasn't just clever experimentation. It confirmed that a vacuum could exist, and that it behaved in a predictable, measurable way. Nature did not abhor it after all. Then came Robert Boyle in England. In the 1650s, working with Robert Hooke, Boyle built some of the first air pumps capable of creating low-pressure environments. They experimented with flames, sound, animals, and physical materials under reduced air pressure. Flames sputtered. bells became silent. Small animals struggled, not because of unnatural forces, but because the air itself, the thing once considered weightless, was necessary for life and sound. Boyle's work helped establish the idea that gases have pressure, volume, and temperature relationships, what we now call Boyle's law. This was a scientific turning point. The vacuum transformed from philosophical curiosity to experimental reality. By the end of the 17th century, the vacuum had become an accepted concept in classical physics. Yet it wasn't mysterious. It wasn't seen as dynamic or energetic. It was simply the absence of matter and air, nothing more. Classical physics treated vacuum like a silent stage on which the real actors, forces, masses, fields, performed. Isaac Newton, in the late 1600s, saw space as an absolute, empty backdrop. Light travelled through it as waves. Though no medium was required in his formulation, motion was possible in a vacuum because forces acted at a distance. But this idea didn't fully settle. In the 1800s, a new concept emerged: the luminiferous ether, an invisible medium that supposedly filled all of space and allowed light to propagate as a wave. Many scientists believed this ether was real because waves, like sound and water waves, need a medium, so surely light did too. Once again, emptiness became suspicious. But this time, it didn't last long. The Michelson-Morley experiment of 1887 famously failed to detect any trace of ether. Their result was puzzling at the time, but it paved the way for Einstein's work. In 1905, Einstein's theory of special relativity successfully described light without any medium at all. Space didn't need an ether. Light didn't need a background substance. The vacuum was back to being nothing. At least that's what classical physics believed. A clean, perfect emptiness. A place where nothing happens. A neutral background with no active behaviour. But this classical view was destined to collapse, because in the early 20th century, a new field emerged that changed everything: quantum mechanics. And later, its modern extension, quantum field theory, would reveal that the vacuum isn't silent, isn't empty, and isn't simple. It has structure. It has fluctuations. It contains the lowest possible energy the universe allows. And the Casimir Effect, the invisible pressure that comes from nothing, is one of the most direct demonstrations of this new quantum vacuum. Before we reach that point, we need to look at how this quantum idea emerged, and why physicists eventually realized that even the emptiest space in the universe can never be truly empty. If the classical idea of a vacuum was a quiet, empty backdrop, a clean stage on which the universe performed, the early 20th century began tearing up the stage itself. By the 1920s and 1930s, physics was undergoing one of its most dramatic transitions. Old ideas were not just being questioned, they were being replaced by something entirely new, a framework that said the world wasn't built from tiny billiard ball particles moving through empty space, but from something far more abstract and far more fundamental. To understand the Casimir effect, we have to walk into this transition, the birth of quantum field theory. But before fields became the main characters, the story began with quantum mechanics, a theory that quietly overturned everything scientists thought they understood about emptiness. At the beginning of the 20th century, Newtonian mechanics still dominated everyday thinking. Even as electricity, magnetism, and thermodynamics matured, the universe was still imagined as a collection of particles with definite positions and motions. But the discovery of the electron in 1897, the puzzling behavior of atoms, and a series of experiments on light forced physicists to accept that classical physics was no longer enough. The old rules broke down. Atoms radiated energy in discrete amounts, not continuously. Particles behaved like waves, and waves behaved like particles. Even empty space began showing strange mathematical properties. By 1925, Werner Heisenberg, just 23 years old, helped launch the new quantum revolution with a mathematical reformulation of physics that initially seemed almost alien. Instead of describing particles as small objects moving along defined paths, Heisenberg used mathematical arrays, matrices, to represent physical quantities. His approach captured atomic behavior, but it didn't look anything like the physics people were used to. Shortly after, Erwin Schrödinger introduced wave mechanics, a picture in which particles weren't points at all but spread out waves described by a wave function. Paul Dirac then unified these competing approaches into a single framework and in the process laid the groundwork for something bigger. The idea that particles were not fundamental but rather excitations of underlying fields. This was the seed of quantum field theory. To understand why this shift happened, imagine looking at an electron. Classical physics treats it like a tiny speck moving through space. Quantum mechanics complicates that, insisting the electron does not have a definite position unless measured. But quantum field theory goes further. It says the electron is not a standalone object at all. There is an electron field that fills all of space, every point, everywhere. And what we call an electron is simply a small, localized vibration in that field. Fields were not new. Maxwell's equations from the 1800s already described electric and magnetic fields as real physical entities spread throughout space. You can't isolate an electric field in a jar, but its effects are real. Quantum field theory extends this idea to everything. There is a field for electrons, a field for quarks, a field for photons, a field for the Higgs boson, a field for every known particle type. Space, therefore, is not empty. It is an ocean of fields. Matter, light, forces, all of it arises from fields interacting. The solid world we experience is simply the result of stable vibrations in these fields. And the vacuum? The vacuum becomes the lowest energy state of all these fields. But lowest energy does not mean no energy. This is the key to the Casimir effect. In classical physics, if you take away all matter, all particles, and all radiation, you should be left with a perfectly calm, featureless void. The energy would be zero. Dead silent. Quantum mechanics disagrees. Heisenberg's uncertainty principle, introduced in 1927, states that certain pairs of physical quantities cannot both have definite values at the same time. One of those pairs is energy and time. And because of this relationship, the energy of a system cannot settle to exactly zero. If it did, both the energy and its rate of change would be precisely known, a direct violation of quantum rules. So even when you remove every particle and freeze everything to absolute zero, the fields cannot sit perfectly still. They must fluctuate. The vacuum becomes a restless environment where tiny amounts of energy appear and disappear. These fluctuations are extremely rapid and extremely small, but they are unavoidable. This minimum irreducible amount of energy is called zero-point energy, the baseline hum of the universe. If you were able to detect these fields directly, you would hear a faint static everywhere, not because something is there, but because nothingness itself refuses to be silent. The concept of vacuum fluctuations began emerging in the late 1920s and early 1930s, when a handful of physicists explored what quantum mechanics implied about empty space. Heisenberg, Wolfgang Pauli, Pascual Jordan, and Paul Dirac were among the first to confront these strange conclusions. Heisenberg introduced the uncertainty principle, which implies non-zero vacuum energy. Pauli argued that electromagnetic fields must exhibit zero-point fluctuations, even though the theoretical energy densities seemed unreasonably large. Jordan supported the idea that fields themselves should be quantized. And Dirac introduced the Dirac-sea, a theoretical model in which negative energy states fill the vacuum, predicting the existence of antimatter. These early results were mathematically shocking. Calculations of vacuum energy suggested enormous values, large enough to warp space-time dramatically. Pauli joked that if the vacuum energy were real, the universe would curl up to the size of a pea. But regardless of the numerical issues, the conceptual shift was clear. The vacuum could no longer be considered empty. To avoid misleading imagery, it's important to clarify what vacuum fluctuations actually are. They are not literal particles shooting in and out of existence like sparks in a dark room. They are temporary disturbances in the underlying fields permitted by the uncertainty principle. They behave as if particles had appeared briefly, but they are not physical objects in the classical sense. They don't travel, persist, or collide. They are momentary ripples, not miniature pieces of matter. The fields fluctuate, and those fluctuations have measurable consequences. When boundaries or conditions change, the allowed fluctuations change as well. This is where the Casimir effect begins. Altering the structure of the vacuum restricts which fluctuations can occur, and that restriction changes the vacuum's energy, producing a force. One surprising outcome of quantum field theory is that the vacuum reacts to changes. If you accelerate a mirror quickly enough in a vacuum, you can generate real photons from vacuum fluctuations, the dynamical Casimir effect demonstrated in 2011. If you place a charged particle in a vacuum, fluctuations in the electromagnetic field modify how the particle behaves, leading to the Lamb shift, measured in 1947. And if you place two neutral metal plates extremely close together, the electromagnetic fluctuations between them differ from those outside, causing the plates to experience a force. This is the Casimir effect predicted in 1948. These aren't philosophical curiosities, they are measurable, real, and experimentally verified. Even in the absence of matter, space itself behaves like an active system. It responds to boundaries, motion, and the presence of fields. By the mid-20th century, physicists had accepted that particles were excitations of fields. Quantum field theory grew steadily, from Dirac's electron field to the quantization of electromagnetism, and later to the standard model of particle physics. QFT now forms the backbone of modern physics, describing how atoms behave, how nuclear reactions occur, how particles scatter in accelerators, how forces arise, and why the vacuum is never truly empty. In this framework, the Casimir effect is no longer mysterious. It is a natural consequence of how the vacuum responds to changes in boundary conditions. Restrict the field, alter the allowed fluctuations, change the vacuum energy, and you produce a force. At the heart of all this lies Heisenberg's uncertainty principle. It ensures that the fields cannot ever settle into absolute stillness. Even at the lowest possible energy state, some motion remains. Without the uncertainty principle, the Casimir effect would not exist. Zero-point energy would vanish. The entire quantum vacuum would collapse into perfect silence. But the universe doesn't allow perfect silence. The vacuum must stay active, fields must fluctuate, energy cannot be pinned down with exact precision. And because of this unavoidable restlessness, empty space becomes one of the most dynamic and surprising environments in all of physics. By the time Hendrik Casimir proposed his idea in 1948, the groundwork was ready, quantum fields were understood. Zero-point energy was accepted, vacuum fluctuations had known consequences. Casimir's insight was straightforward. If the vacuum is full of fluctuating fields, then placing boundaries inside it must change those fluctuations, change the fluctuations, and you change the vacuum energy. Change the vacuum energy, and you get a force from nothing, a pressure generated by empty space. And that realization would soon lead to one of the most subtle and fascinating predictions in physics, a prediction that took almost 50 years to measure. In the late 1940s, the world of physics was still recovering from one of the most intense periods of scientific and technological acceleration in history. Quantum mechanics had reshaped the foundations of science. Nuclear physics had changed global politics. Radar, electronics, and vacuum tube engineering had advanced at a dizzying pace during the Second World War. Laboratories across Europe and the United States were trying to rebuild their research programs, redirecting brilliant minds from military work back toward fundamental science. It was in this environment, at Philips Research Laboratories in Eindhoven, that a Dutch physicist named Hendrik Casimir stumbled onto an idea that seemed almost absurd at first. A force created not by electricity, not by magnetism, not by gravity, but by the vacuum itself. Casimir had already built an impressive reputation by the time he arrived at Philips. Born in 1909, he studied under some of the most influential physicists of the early 20th century, including Wolfgang Pauli and Niels Bohr. He absorbed the rapidly evolving ideas of quantum mechanics directly from the people creating them. By the mid-1940s, he was one of Europe's strongest experts in theoretical physics, especially in quantum electrodynamics, the theory of how light and matter interact. Philips, known mainly as an electronics company, also housed one of the leading industrial research labs in Europe. Their scientists worked on everything from early electronics to vacuum tubes, superconductivity, materials science, and emerging ideas about quantum systems. Casimir joined the lab in 1942, and soon after the war ended, he found himself exploring problems that sat at the boundary between engineering and fundamental physics. The motivation for what eventually became the Casimir Effect began with a very practical question. Philips engineers were studying tiny electromagnetic forces inside vacuum tubes and other micro-scale devices. They wanted to understand subtle interactions between charges, currents, and conducting surfaces. At extremely small separations, classical explanations seemed incomplete. The behavior of electrons and fields inside confined geometries didn't always match predictions. Casimir and his colleague Dirk Polder were examining how atoms and molecules interact with surfaces. Specifically, they were analysing a subtle effect known as dispersion forces, forces that arise due to fluctuations in the electromagnetic field, even between neutral objects. These forces were well known in the context of chemistry and materials science, but the full quantum explanation was still developing. One day, while exploring a particular model, Casimir asked a natural question: what happens if you take two perfect neutral conducting plates and place them extremely close together in a vacuum, not touching, not charged, not magnetized, just sitting there, parallel, separated by a microscopic distance? Classical physics gave a simple answer: nothing. No charge, no current, no interaction. The plates should remain completely indifferent to each other. Quantum physics did not like this answer. Casimir suspected that the vacuum between the plates would behave differently from the vacuum outside them. The idea was rooted in quantum field theory, although the theory at the time was not as developed as it is today. Still, enough was understood to suggest that empty space filled with fluctuating electromagnetic fields would respond to boundaries. Metal plates are not passive. They impose strict conditions on electromagnetic fields. Inside a conductor, the electric field must vanish. Along the surface, certain components must cancel out. These rules restrict the types of electromagnetic waves that can exist near or between conducting plates. Some wavelengths fit in the gap, others do not. To visualize this, imagine holding two mirrors facing each other. Light waves bouncing between them can only form standing waves with specific allowed wavelengths. Anything that doesn't fit the geometry cannot exist as a stable mode. Now, replace light waves with vacuum fluctuations, the ever-present jittery behavior of the electromagnetic field. The same restrictions apply between two plates separated by a tiny distance. Only certain fluctuation modes can exist. Outside the plates, every wavelength is allowed. Inside, the spectrum is limited. This means the vacuum energy, the baseline energy associated with fluctuations, is different in the two regions. Outside the plates, the vacuum has a higher density of available modes. Inside, it has fewer. And if one region has more energy than the other, a pressure difference must exist. The region with higher energy pushes harder. In this case, the outside vacuum has more allowed fluctuations and therefore exerts more pressure. Inside, fewer modes means less pressure. The result is an inward force pushing the plates together. A force created not by matter, not by charge, but by the structure of empty space. Casimir realized this almost immediately, and the more he explored the idea, the more convincing it became. He derived a mathematical expression for the pressure between two perfectly conducting plates. The force was incredibly small, far too small to measure with 1940s technology, but it was unmistakable. The vacuum should push the plates together. It was a stunning conclusion. Here was a force with no classical counterpart, a force with no source, no field lines, no charges, a force emerging purely from the absence of certain quantum fluctuations. And yet, it made sense. As strange as it sounded, it followed directly from the rules of quantum electrodynamics. Casimir's work with Polder had already brought him close to this boundary. Their studies of dispersion forces revealed that fluctuating electromagnetic fields could generate real forces even between neutral atoms. What Casimir discovered was a similar phenomenon, but applied to macroscopic surfaces rather than molecules. Instead of atoms polarizing each other, it was the vacuum itself modifying the energies of confined fields. The context around the discovery is also important. In the late 1940s, quantum electrodynamics was struggling. Mathematical infinities plagued the theory. Renormalization, the technique that made QED workable, was still being debated. Many physicists were frustrated by the difficulty of making sense of quantum fields. In that environment, predicting a new physical effect from the vacuum was bold. Casimir submitted his prediction in 1948. At first, many scientists found it hard to believe. A force from nothing, a pressure created by empty space. It sounded almost metaphysical. But the more people examined the mathematics, the more solid the idea became. Casimir's reasoning was straightforward, elegant, and built on the core principles of quantum theory. It did not rely on speculation or exotic assumptions. It simply acknowledged that the vacuum is a physical system, and that physical systems change when their boundaries change. In a way, Casimir did not invent the effect. He revealed it. He followed the logic of quantum theory to its natural conclusion. The reaction was mixed. Some physicists were fascinated, others dismissed it as a theoretical curiosity that might never be measured. The predicted force was far too small for any experimental setup of the time. It required plates aligned with extreme precision, separated by distances smaller than a micrometer, isolated from vibration, dust, and surface imperfections. Measuring it in the 1940s was impossible. But impossible does not mean unimportant. The prediction stood as a quiet reminder that quantum mechanics applied even in the absence of matter, that the vacuum was not a blank canvas, but a dynamic player in the physics of the universe. Casimir himself did not foresee the effect becoming widely known. He expected it to remain a footnote in theoretical studies, perhaps relevant in very specialized contexts. He could not have predicted that decades later it would become central in nanotechnology, quantum engineering, and cosmology. His insight grew into one of the clearest demonstrations of what quantum field theory says about the vacuum. It showed that empty space has measurable properties. It showed that the universe cannot maintain silence, even when stripped of everything we consider physical. It showed that boundaries matter, that geometry itself affects the vacuum. And it all began with a simple question in a research lab, posed by a physicist trying to understand why neutral atoms and surfaces experience forces in the absence of charge. The kind of question that seems small at first glance, but opens a door to something much larger. Two uncharged plates, quietly suspended in a vacuum, experiencing a force with no classical explanation. A pressure emerging from nothing, or rather, from the fact that nothing is not what we thought it was. Years later, the effect would finally be measured, marking a turning point in experimental physics. But even before the measurement, the idea itself reshaped our understanding of the vacuum. It demonstrated that emptiness has consequences, that the vacuum is active, that quantum physics applies everywhere, not just inside atoms. Casimir didn't just predict a force, he changed the way physicists think about nothingness. When Hendrik Casimir published his prediction in 1948, the reaction from physicists was a mix of curiosity and skepticism. The mathematics was elegant, the reasoning clear, but there was a serious problem. The force he described, this strange pressure created by the vacuum, was extraordinarily small, so small that it seemed almost unreachable with the technology of the time. The idea was fascinating, but the practical reality of testing it felt like trying to measure the weight of a feather using a steam locomotive. The scale mismatch was overwhelming. To appreciate how difficult it was, imagine the basic requirement. You need two metal plates placed extremely close together, close enough that the difference in allowed vacuum fluctuations inside and outside becomes significant, not millimeters, not micrometers, but separations on the order of nanometers. That's a distance smaller than the wavelength of visible light, a distance where dust particles are gigantic, where a single vibration from the floor can ruin an experiment, where even the slightest tilt of a plate changes the force dramatically. And then, once you've brought these plates dangerously close, you need to make sure they remain perfectly parallel. If they tilt even by a fraction of a degree, the gaps across their surfaces change. One side might be 100 nanometers apart, while the other side is 500 nanometers apart, and the force becomes impossible to calculate or measure properly. Alignment to this degree was far beyond the mechanical precision of 1950s laboratories. Surface imperfections were another nightmare. Real metal plates are never perfectly smooth. Under a microscope, even the cleanest polished metal looks like a rugged mountain landscape. Peaks and valleys are everywhere. When two such surfaces are brought within nanometers of each other, those imperfections dominate the physics. Instead of a smooth, uniform force predicted by Casimir, the surfaces experience a chaotic patchwork of local interactions. It becomes difficult to know whether any force measured is actually the Casimir effect, or just a surface defect grabbing onto its neighbour. The materials used at the time weren't ideal either. Casimir's original formula assumed perfectly conducting plates, the kind that reflect electromagnetic waves flawlessly. No real metal behaves this way. Conductivity depends on frequency, impurities, surface oxidation, and temperature. At nanometer scales, these imperfections significantly alter the vacuum energy between plates. But in the mid-20th century, no one knew how to include these real-world corrections accurately. Even if the plates could somehow be made sufficiently smooth, aligned, and conductive, another major problem remained. Vibrations, human footsteps, a truck driving down the street, a distant door closing, even the building itself expanding and contracting during the day. All of these introduce vibrations many orders of magnitude larger than the Casimir force experiments that seemed stable to human senses were violently unstable at the level required for measurement. And then there was dust. Ordinary household dust particles range from a few micrometers to tens of micrometers across, thousands of times larger than the separation between plates needed for detecting the Casimir effect. A single naturally occurring speck is enough to completely alter the geometry. A bit of smoke from a nearby cigarette, a small fibre from clothing, or a trace of skin oil on a plate could ruin the experiment. In short, the Casimir effect was theoretically beautiful, but practically invisible. Physicists in the 1950s and 1960s tried anyway. They attempted using ultra-thin foils, polished metal plates, and even early forms of vacuum deposition to create smoother surfaces. But the equipment available at the time was simply not precise enough. The vacuum chambers were too crude, the alignment mechanisms too loose. The measurement instruments, usually torsion balances or mechanical levers, were nowhere near sensitive enough to detect forces as weak as the Casimir prediction. One of the earliest attempted measurements used thin gold-coated plates suspended inside a sealed chamber. The idea was to detect the tiny inward pull using a simple mechanical sensor, but the plates warped slightly under their own weight, bending just enough to break the required symmetry. What the researcher thought would be a pair of perfectly parallel surfaces was, in reality, closer to two shallow bowls. The Casimir force, if present, was drowned in noise. Another attempt involved bringing a small metal sphere close to a flat plate instead of using two parallel plates. This geometry is easier to manage because it avoids the need for perfect alignment. A sphere is always parallel to a plane at the point of closest approach, but even this approach failed. The spheres available at the time were not perfectly spherical. Under magnification, they looked lumpy, their surfaces were irregular, the coatings were uneven, and the force predicted in a sphere-plane setup is still extremely small, well below the sensitivity of the instruments then available. Through the 1960s and 1970s, more theoretical refinements were published. Physicists began incorporating effects like finite conductivity, surface roughness, and temperature corrections into the Casimir force equations. They realized that Casimir's original expression applied strictly to perfect conductors, which do not exist. The real world introduces complexities. Metals reflect some frequencies well, but absorb others. Surface patches with different work functions create tiny electric potentials. Polymer films absorb moisture, and thin films can bend or wrinkle. Researchers such as Lifshitz, Dzieloszynski, and Pitaevsky developed a more accurate theoretical framework known as the Lifshitz theory. Published in the 1950s and early 1960s, it allowed the Casimir effect to be calculated for real materials with real electromagnetic properties. Instead of assuming perfect reflection, the Lifshitz model used the dielectric functions of materials to determine how the vacuum fluctuations behaved around them. This was a major advance, but it made the predictions harder to test experimentally. In a sense, the Casimir effect became a theoretical playground during these decades. Papers refined the equations. Researchers explored how the force behaved for different materials, shapes, and temperatures. But none of these theoretical developments solved the main barrier, the lack of experimental precision. No one doubted that Casimir's reasoning was correct. The challenge was simply that nature did not cooperate with the delicacy required. It was like trying to detect the weight of a virus using a kitchen scale. The scale isn't wrong. It's just nowhere near sensitive enough. By the late 1970s, some laboratories began to acquire more advanced equipment thanks to developments in semiconductor research, atomic force microscopy, and vacuum technology cleanrooms became more common. Scientists gained access to tools that could smooth surfaces with higher precision. Piezoelectric actuators allowed for ultrafine control of position, but even with these tools, the Casimir force remained just out of reach. The problem was not simply to position two objects nanometers apart, it was to position them nanometers apart, keep them parallel, suppress all vibrations, eliminate all stray charges, remove all dust, and measure an extremely weak force without disturbing the system. Each of those requirements was nearly impossible by itself. Combined, they formed an experimental barrier that would take decades to overcome. Even so, these years were not wasted. Theoretical work continued refining the Casimir effect, predicting new geometries and new materials where the force might be more pronounced. Researchers explored how temperature affects the force, how surface roughness alters it, and how the effect behaves in different frequency regimes. By the 1980s, the pieces were finally beginning to fall into place. Advances in torsion pendulums, extremely sensitive devices capable of detecting tiny forces, suggested new approaches. Improvements in vacuum technology allowed for cleaner environments. And the rise of microfabrication techniques, originally developed for computer chips, provided the precision needed to create surfaces smoother than anything available a generation before. Physicists were getting closer. Theoreticians could calculate the effect more accurately. Engineers could build better tools. Materials scientists could produce cleaner, more uniform metals. The Casimir effect was waiting patiently, its tiny force pulling plates together quietly, invisibly, for half a century. It was no longer a question of whether the effect existed. It was a question of who would finally measure it, and how. Because measuring the Casimir effect required not just precision and skill, but creativity. It required thinking differently about how to detect a force that seemed too small to matter. And eventually, in the late 1990s, one physicist in Washington state would break through the barrier, using a device that looked simple, but operated with extraordinary sensitivity. The first successful measurement would change everything, and it would confirm once and for all that the vacuum is not empty. By the mid-1990s, the Casimir Effect had lived almost half a century as a clever theoretical prediction. Physicists accepted it in principle, quantum field theory implied it. The mathematics was solid, but no one had ever truly seen it. Not directly, not cleanly, not in a way that left no ambiguity. To many scientists, the Casimir Effect was similar to hearing rumours of a faint sound in a distant forest. You know something is there. You even know what should be causing it, but until someone records it clearly, there is always a sliver of doubt. Maybe the sound is real. Maybe it's just wind. Measuring a force created by empty space itself required a level of precision that earlier decades simply couldn't reach. Vibrations, dust, temperature fluctuations, surface imperfections, all of them overwhelmed the effect. But by the early 1990s, technology had finally matured. Atomic force microscopes existed. Clean rooms were more common. Precision positioning systems could control movements below a nanometer. Materials were purer and smoother. And at the University of Washington in Seattle, a physicist named Stephen Lamoreaux decided it was time to try again. Lamoreaux was not the first to attempt the measurement, but he was the first to approach it with a combination of modern instrumentation and a clever twist on the original geometry. Instead of trying to align two flat plates, one of the most impossibly delicate tasks in experimental physics, he used a sphere and a plate. This geometry simplified everything. A sphere is always parallel to a plane at the point where they are closest. No need for perfect alignment, no need to maintain parallelism. The contact region behaves predictably, and the theory describing the force between a sphere and a plate had already been refined through decades of work. Lamoreaux needed one more ingredient: sensitivity. The force he wanted to measure was incredibly tiny. Even at separations of a few micrometers, the expected Casimir force between a metal sphere and a metal plate is only about a few hundred piconewtons. That is roughly the weight of a single human red blood cell resting on your hand. Measuring something that's small requires a detector so delicate that even a slight breeze, a small earthquake hundreds of miles away, or the thermal motion of the apparatus could drown the signal. Lamoreaux built his experiment around an instrument that has a long and storied history in physics, the torsion pendulum. A torsion pendulum is conceptually simple. Imagine a horizontal bar suspended in its center by a thin wire. If you apply a tiny sideways force to either end of the bar, the wire twists slightly and then tries to untwist, acting like a rotational spring. The twist angle is proportional to the force. It's a classic tool for detecting incredibly small forces. Henry Cavendish used a torsion balance in 1797 to measure the gravitational constant, detecting the minuscule attraction between lead spheres. Over 2 centuries later, Lamoreaux revived this technique for a force far stranger than gravity. His setup consisted of a small, highly polished metal sphere attached to one end of the horizontal bar. A flat metal plate was positioned near the sphere, with the separation controlled by piezoelectric actuators, capable of moving in precise increments measured in nanometers. As the plate moved closer to the sphere, the Casimir force between them grew. This force pulled the sphere slightly toward the plate, twisting the torsion wire. The twist was then detected using a sensitive optical or electrical readout system. The brilliance of Lamoreaux's design lay in its simplicity. Instead of forcing two surfaces to maintain perfect contact at a uniform separation, he used geometry to avoid the hardest problems. Instead of pushing materials or measurement techniques to their limits in multiple dimensions, he eliminated many of the traditional sources of error. This let him focus his attention on suppressing vibrations, stabilizing temperatures, and removing static charges, each of which could mask or distort the force he sought. Dust, as always, remained a threat. Lamoreaux worked in a clean environment and handled materials carefully to avoid contamination. Temperature changes could cause subtle expansions or contractions in the apparatus, so the entire experiment was thermally isolated. Vibrations from footsteps, elevators, road traffic, or even distant machinery could twist the pendulum, so the apparatus was mounted on a vibration-damping platform, sometimes floating on air or resting on isolation supports. Even with all this preparation, controlling stray electrostatic forces was one of the biggest challenges. In real materials, microscopic patches of slightly different electrical potential form on surfaces even when the objects are nominally uncharged. These patch potentials can attract or repel each other and mimic or obscure the Casimir force Lamoreaux carefully measured and corrected for these effects, adjusting voltages to nullify unwanted electrostatic interactions. Only after eliminating these competing influences could the vacuum force reveal itself. When Lamoreaux ran his experiment, he monitored the torsion pendulum as the sphere approached the plate. The twist began to increase, slowly at first, then more noticeably. The amount of rotation matched exactly what the modified Casimir theory predicted for the materials, geometry, and distances he used. The force was there, it was real, it followed the curve expected from vacuum fluctuations. Nothing else explained the data. In late 1996 and early 1997, Lamoreaux repeated the measurements again and again, refining the distance control, improving the signal-to-noise ratio, and ensuring that the effect wasn't caused by stray charges, air currents, thermal drifts, or mechanical quirks of the apparatus. Every time, the result remained clear. As the sphere approached the plate, an attractive force appeared, stronger at smaller separations, exactly matching the Casimir prediction. The first successful measurement of the Casimir effect was published in Physical Review Letters in February 1997. Suddenly, nothingness became measurable. For the first time, a human instrument had reached into empty space and detected the pressure of the vacuum. Casimir's once abstract idea had crossed over from mathematical argument to experimental fact. The vacuum, the supposed nothing in which physics takes place, had revealed itself as a physical system with measurable behaviour. This was a milestone in modern physics. It confirmed not just the Casimir effect, but the deeper principle behind it. The vacuum is not empty, it has structure. It has energy. It responds to boundaries. It pushes and pulls on matter, even when no charges or fields are present. Lamoreaux's measurement also validated decades of theoretical work refining quantum field theory. Zero-point energy, vacuum fluctuations, and the concept of the vacuum as a dynamic environment had long been pillars of theory, but seeing experimental evidence on a lab bench transformed these ideas from mathematical necessities into physical realities. The accuracy of Lamoreaux's result was impressive. His data matched theoretical predictions within about 5%, remarkable given the experimental challenges. Later experiments using micro-electromechanical systems, MEMS, atomic force microscopes, and more advanced materials improved the precision even further. But Lamoreaux's work remains the moment when the Casimir effect stepped clearly into the world of measured phenomena. One of the most striking consequences of his measurement was psychological. Physicists already knew that the vacuum was active, but the ability to detect that activity directly was transformative. For students of quantum mechanics, the idea that nothingness had energy could feel abstract and counterintuitive. Lamoreaux's experiment changed that it turned an abstraction into a force you could plot on a graph, write down with measured units, and replicate in independent laboratories. It also opened the door to a much wider range of experimental investigations. Researchers began exploring variations of the Casimir effect using different materials, different shapes, different temperatures, and even different media. They found that the Casimir force could be altered, reduced, enhanced, or even made repulsive in certain configurations. This suggested future applications in nanotechnology, where such forces can dominate the behaviour of tiny mechanical structures. But the most profound legacy of Lamoreaux's work lies in what it revealed about the universe. Empty space is not the absence of reality. It is a background state full of fluctuating fields. It is an environment that exerts pressure, responds to geometry, and influences matter at the smallest scales. All of this was hidden from direct view until a single experiment in Seattle made it visible. Lamoreaux didn't just measure a tiny force, he measured the quantum structure of the vacuum. He provided direct evidence that even when everything else is removed, all matter, all radiation, all fields, the universe continues to behave, it continues to fluctuate, it continues to exert subtle but measurable influences. The Casimir Effect, once a theoretical curiosity, became a cornerstone of modern experimental physics. And it all began with a torsion pendulum, a polished sphere, a flat plate, and the determination to measure a force that most people thought was beyond reach. By the time Stephen Lamoreaux measured the Casimir effect in 1997, physicists already understood that vacuum fluctuations were more than just a theoretical curiosity. But what most engineers didn't expect was that this force, so subtle, so impossibly small at human scales, would become a major obstacle in some of the most advanced technologies ever built. As devices shrank into the realm of micrometers and nanometers, the Casimir force, once too tiny to detect, suddenly became a dominant player. What was invisible in the macroscopic world became unavoidable in the microscopic one. Modern nanotechnology and micro-electromechanical systems, usually abbreviated as MEMS and NEMS, rely on components so small that a dust particle looks like a mountain and a fingerprint looks like a landscape. In this tiny world, classical physics doesn't tell the whole story anymore. Forces that mean nothing to us on ordinary scales begin to matter. Surface tension becomes stronger than weight. Electrostatic forces can overwhelm mechanical springs. Even Brownian motion, the random jitter of atoms in the environment, can shake components around like gentle waves rocking a boat. And then there is the Casimir force. It doesn't require voltage. It doesn't require contact. It doesn't require moving parts or external fields. It arises simply because empty space behaves differently at these scales. For engineers designing microstructures, this force can be both fascinating and frustrating. Imagine you have two tiny metal beams inside a MEMS device separated by just a few tens of nanometers. Under ideal conditions, these beams should vibrate freely, transmit signals, or act as mechanical switches, but if they get too close, the Casimir force begins to pull them together. Unlike static electricity, which can be neutralized by grounding or charge balancing, the Casimir force can't be turned off. It's built into the structure of the vacuum itself. This leads to a problem known as stiction, a combination of static and friction. It happens when two components inside a microdevice snap together and stick, unable to separate. Once that happens, the device is ruined. For consumer electronics, that means failure. For precision scientific instruments, it means losing a measurement. For research labs designing prototypes, it means going back to the drawing board. Stiction is one of the biggest headaches in MEMS engineering. At the nanometer scale, the Casimir force can be stronger than the mechanical restoring force of tiny springs or beams. A part that is supposed to move freely becomes stuck permanently. In larger devices, gravity or structural rigidity counteracts unwanted forces, but at nanoscales, the Casimir attraction can surpass everything else. The effect becomes even more pronounced when surfaces are smooth, and nanotechnology demands extremely smooth surfaces. Rough surfaces scatter waves and disrupt interactions, but smooth surfaces allow vacuum fluctuations to exert maximum influence. Ironically, the better engineers get at polishing and fabricating components, the more pronounced the Casimir effect can become. This creates a kind of engineering paradox. To make microdevices more reliable, you want smoother surfaces, but smoother surfaces increase the quantum attraction between them. A similar tension appears when components get thinner. Thin beams respond more easily to forces. They bend more readily. They collapse under pressures that thicker components can resist, and the Casimir force scales strongly with separation. The closer the pieces, the stronger the pull. At just a few nanometers apart, the force becomes surprisingly large. Not large by human standards, but large relative to the mechanical strength of the components. These issues show up in devices we rarely think about. The accelerometers inside smartphones, tiny pressure sensors used in medical implants, micro mirrors used in projectors and adaptive optics, nanoscale switches inside research instruments, even components inside hard drives and microchips. If two parts that should never touch find themselves brought together by vacuum pressure, the device fails. Engineers quickly learned that they needed strategies to fight or avoid the Casimir effect. One approach was geometric. Design structures so that surfaces never come close enough to trigger strong quantum attraction. But this is easier said than done. Nanodevices are often designed to operate in extremely tight spaces. Space is expensive at the nanometer scale. Every component must be compact, every motion constrained. Another strategy is to adjust surface properties. Certain coatings alter how electromagnetic fluctuations behave near the surface. By choosing materials with particular dielectric properties, it is sometimes possible to reduce the Casimir attraction between surfaces. Some experiments have even shown that under the right conditions, with carefully selected materials and intervening fluids, the Casimir force can become repulsive instead of attractive. This Casimir repulsion is not a magic fix, but it opens up new engineering possibilities. Surface patterning is another powerful tool. Instead of leaving the surfaces perfectly flat, engineers can introduce microscopic ridges or textures. These patterns disrupt the electromagnetic field configurations, reducing the vacuum pressure between surfaces. It's similar to how dimples on a golf ball influence airflow. Small geometric changes can have a large effect on how fields interact. Temperature also plays a role. Casimir forces depend not only on quantum fluctuations, but also on thermal fluctuations at higher temperatures. In some devices, operating at lower temperatures reduces unwanted forces, but cooling equipment is expensive and often impractical in commercial products. Another strategy involves increasing the stiffness of components. If the mechanical restoring forces are strong enough, they can counter the Casimir pull, but this has limits. Making a device stiffer often means making it larger or thicker, which contradicts the goal of miniaturization. As engineers confronted these issues, something became clear. The Casimir effect wasn't just a theoretical demonstration of quantum field theory. It was a practical engineering challenge. It didn't behave like friction, magnetism, or electrostatics. It was weaker, subtler, but constantly present, and it couldn't be turned off. The challenges extended beyond simple attraction. Tiny variations in material composition could lead to slight differences in Casimir forces across a surface. A patch of oxide on one side of a plate could change the local electromagnetic response. These imperfections created tiny variations in pressure, causing components to drift, tilt, or twist unexpectedly. And unlike gravity or magnetism, the Casimir force is always present in any vacuum environment. For satellites, microthrusters, and space instruments, this means components must be designed with an eye toward how vacuum pressure could subtly alter their behavior over years of operation. In some cases, engineers now account for Casimir forces when designing microactuators, adjusting tolerances and calibrations to avoid unexpected drift. Then there are the surprising consequences in fields outside engineering. In atomic physics, ultra-cold experiments need to bring atoms close to surfaces for trapping and manipulation. When atoms approach within a few hundred nanometers of a surface, Casimir Polder forces, the atom-specific cousin of the Casimir effect, can distort atomic trajectories or destabilize traps. Researchers have to compensate by adjusting laser fields or redesigning the geometry of trapping devices. In precision measurement science, Casimir forces can introduce unwanted noise. Devices like atomic force microscopes, designed to measure tiny forces and surface properties, must deal with the fact that the vacuum between their components exerts pressure. If the goal is to measure a molecular bond or atomic interaction, an unexpected Casimir attraction can contaminate the results. Even biological research encounters the effect. Experiments using microfluidic devices, tiny channels that manipulate cells, molecules, or chemicals, must sometimes account for vacuum-induced forces when designing sensors or surfaces that operate at extremely small separations. The more humanity shrinks its technology, the more the Casimir effect matters. And this reveals something profound about physics. Not all laws scale the same way. Gravity dominates planets and galaxies, but becomes negligible for molecules. Quantum fluctuations are irrelevant for cars and buildings, but dominate when objects are 1,000 times smaller than a grain of sand. The Casimir effect is a reminder that the world behaves differently at different scales. And now that we build machines small enough for quantum forces to matter, the vacuum itself has become part of our engineering landscape. In a way, this marks a full circle moment. Hendrik Casimir predicted the effect while studying interactions that occur at tiny distances. Lamoreaux measured it using an experiment built with extraordinary precision. Today, engineers designing micro-devices must think about Casimir forces as practical challenges, not abstract ideas. Quantum mechanics has moved from chalkboards to microchips. Vacuum fluctuations have shifted from theoretical nuisances to engineering considerations, and empty space is now something that must be accounted for, modeled, simulated, and sometimes even engineered around. The Casimir effect is no longer just a window into the quantum vacuum. It has become a force that shapes technology, limits designs, and occasionally breaks devices. It's a quiet influence, but a powerful one, and as our devices continue to shrink, this invisible pressure, born from nothingness, will remain an ever-present companion. As soon as the Casimir effect was confirmed experimentally in the late 1990s, physicists began revisiting an old question that tends to appear whenever a strange quantum effect becomes real. If the vacuum itself contains energy, can we use it? Could we extract power from nothingness? Could the universe's most subtle force be turned into a technological advantage? To be clear, the Casimir effect is not a source of free energy. It does not violate conservation laws. It does not allow perpetual motion, but because it arises from the structure of the vacuum, it's natural to wonder whether the vacuum might be coaxed into doing useful work. This is where Casimir energy enters the conversation, not the pressure that pushes plates together, but the idea of engineering environments with altered vacuum energy. In simple terms, if you could control the geometry of boundaries, materials, and fields, you could change the vacuum's baseline energy in different locations. That energy difference could, at least in principle, create forces that push or pull objects. For most modern applications, those forces are tiny, far too tiny for propulsion in any conventional sense, but the idea itself that shaping empty space changes the energy of the vacuum opened the door for speculation, and speculation attracts both excitement and confusion. In the late 1990s, NASA briefly funded a small initiative called the Breakthrough Propulsion Physics Program. Led by Mark Millis, the project was never intended to build warp drives or exotic spacecraft. Its purpose was far more modest, to identify and evaluate scientific concepts that, while speculative, were at least grounded in known physics or mathematically self-consistent. If a far-future propulsion concept were ever to be plausible, it needed to be compatible with the laws of nature. Among the ideas explored during the program was Casimir propulsion, the notion that if vacuum energy could be manipulated, perhaps it could produce a push. The concept stems from an intuitive thought experiment. If vacuum energy is lower between two plates than outside them, then creating a configuration where the vacuum energy is asymmetrical around a structure might create a directional force. Think of it like using the vacuum pressure difference to push off one side more than the other. If that could be controlled dynamically, maybe a craft could be propelled without throwing mass backward in a conventional rocket exhaust. But as soon as you dig deeper into the physics, problems appear. The Casimir force is inherently equal and opposite. any force you generate inside a closed system cancels out internally. Moving one plate relative to another changes the energy of the system, but the net effect always sums to zero. If everything remains contained, to create propulsion, you would need a net external force, something that pushes the spacecraft forward without requiring reaction mass. Casimir propulsion, at least in the classical sense, does not do that. It shuffles energy inside a system but produces no net thrust to the outside world. NASA's own evaluations reflected this. The idea was intriguing from a theoretical standpoint, but it did not violate known physics, simply because it didn't do anything physically useful. It was not a loophole. It was a dead end. And yet, the broader idea of vacuum engineering, deliberately shaping vacuum energy, has profound implications in theoretical physics, especially concerning exotic spacetimes. This is where negative energy density enters the discussion. In classical physics, energy density, the amount of energy in a given region, is always positive. But quantum mechanics breaks that rule in certain circumstances. Some configurations of fields, including Casimir-like setups, can produce regions where the effective energy density is lower than the ambient vacuum. If you compare that region to zero-point energy, it appears negative. This doesn't mean that energy is less than zero in an absolute sense. It means it's lower relative to the baseline vacuum. But in general relativity, even that relative negative energy matters. The curvature of spacetime responds to energy density. Positive energy curves spacetime inward. Negative energy curves it outward. And with enough negative energy, exotic geometries, wormholes, warp bubbles, closed time-like curves become mathematically possible. This is where science fiction and physics intersect. In 1988, physicist Kip Thorne and his colleagues published a series of papers analysing whether wormholes could exist in principle. Their conclusion was surprising. General relativity allows stable, traversable wormholes, but only if the throat of the wormhole is held open by matter with negative energy density. Without negative energy, the wormhole collapses instantly. The same applies to the Alcubierre warp drive concept proposed in 1994. The idea behind it is mathematically elegant. Compress space-time in front of a spacecraft, expand it behind, and let the craft ride inside a warp bubble, never violating the speed of light limit locally. But this also requires negative energy, lots of it, orders of magnitude, more than any conceivable Casimir configuration could produce. To be clear, the Casimir effect does create negative energy density relative to the outside vacuum. This is a real physical phenomenon. It has been measured. But the magnitude is tiny, and the energy is localized between plates separated by microscopic distances. You cannot create large-scale negative energy with it. You cannot turn the vacuum into a wormhole stabilizer. And you cannot build a warp drive out of parallel plates. The Casimir effect shows that negative energy density is possible in quantum field theory, but it does not provide a practical way to generate or harness that energy in bulk. This distinction is essential. Mathematically allowed is not the same as physically achievable. Most of the exotic space-time geometries that people imagine, wormholes, warp drives, time machines, rely on enormous amounts of negative energy, not small pockets. Not microscopic regions. They require large-scale distributions of exotic matter that, as far as we know, cannot exist in usable forms. Every real-world attempt to generate macroscopic negative energy runs into one of three barriers. The energy is too small. Casimir energies are minuscule compared to the gravitational or electromagnetic scales required to shape spacetime. The energy is too localized. Negative energy regions created by quantum effects exist only in tiny, constrained geometries, not in open, spread-out volumes. Quantum inequalities limit exploitation. Physicists like Ford and Roman showed that quantum field theory places strict limits on how much negative energy can exist, for how long you can't accumulate it. You can't extend it. It appears briefly and vanishes. These constraints are like nature's way of saying, yes, negative energy is possible, but you're not going to build a starship out of it. This is not to discourage curiosity. theoretical work on exotic energy densities has led to deeper understanding of both quantum fields and general relativity. Exploring the boundaries helps clarify which futures are physically possible and which are not. But it's important to separate two categories: real science. The Casimir effect is measurable. It produces negative energy density relative to the vacuum. Vacuum energy depends on geometry and boundary conditions. Quantum fields allow local fluctuations and exotic states. These phenomena influence nanotechnology, materials, science, and cosmology. Speculative fiction, using Casimir plates to power spacecraft, building warp bubbles with tabletop devices, creating traversable wormholes through engineered vacuum, harvesting zero-point energy as a limitless power source. The line between these categories is not philosophical. It is mathematical and experimental. A tabletop experiment cannot destabilize spacetime. A micrometer-scale Casimir cavity does not contain usable energy. Zero-point energy cannot be extracted as fuel, but speculation, when grounded in real physics, can inspire deeper questions. The Casimir effect teaches us that the vacuum is not inert. It responds to shape, it contains energy, it can exert pressure, it can bend in subtle ways. This cuts both ways. It disproves certain science fiction fantasies but opens other doors. If we ever find practical methods for manipulating vacuum energy in ways compatible with quantum field theory and thermodynamics, it will most likely come from advances in materials science, nanotechnology, and condensed matter physics, not from wormhole engines. The vacuum is full of structure, but that structure is tightly constrained by the rules of quantum fields and relativity. The Casimir effect sits at the boundary between what is real and what is imagined. It reminds us that nothingness is more complex than it appears, but also that physics is stricter than our dreams. Even so, the fact that a measurable force can arise from empty space is astonishing enough on its own. It tells us that the universe hides layers we are still learning to understand, and sometimes those layers shine brightest, not in grand speculative ideas, but in the quiet, precise experiments that reveal how subtle forces shape reality. When physicists talk about vacuum energy in the context of the Casimir effect, the conversation usually stays at the microscopic scale: nanometers, micrometers, tiny cavities, and tiny forces. But the moment you lift the discussion into cosmology, vacuum energy turns into one of the largest, strangest, and most embarrassing problems in all of physics. The Casimir effect shows, beyond any doubt, that the vacuum has energy. Zero-point energy is not a metaphor or a mathematical trick. It is measurable. It pushes metal plates together. It affects real experiments. It alters atomic energy levels. In laboratories, zero-point energy is just another quantum phenomenon, subtle, precise, and under control. But when you try to calculate the total amount of zero-point energy in the universe using the rules of quantum field theory, something goes terribly wrong. You get the wrong answer, not by a factor of 2, not by a factor of 1,000, but by a factor of 10 raised to the 120th power. This mismatch is often described as the largest discrepancy between theory and observation in the entire history of science. To understand how this happened, it helps to step back for a moment and look at the history of vacuum energy in cosmology. Einstein's equations of general relativity include a term called the cosmological constant, a kind of energy density built into the structure of space-time. He originally introduced it in 1917 because he believed the universe was static and unchanging. Without a cosmological constant acting as a repulsive force, the universe predicted by his equations would collapse under its own gravity. When Edwin Hubble discovered the expansion of the universe in 1929, Einstein abandoned the constant and supposedly called it the biggest blunder of my life. But the idea did not disappear. It simply waited for physics to catch up. In the late 1960s, Soviet physicist Yakov Zeldovich made a bold proposal. Maybe the cosmological constant wasn't just a mathematical convenience. Maybe it represented the energy of the quantum vacuum itself. If quantum fields have zero-point energy, energy that exists even at absolute zero, then that energy should contribute to the overall energy density of empty space. And in general relativity, energy density curves space-time. That means vacuum energy should affect the expansion of the universe. It was a clever idea and seemed consistent with the emerging understanding of quantum fields. Then Zeldovich tried to calculate the number. That was the moment everything fell apart. Quantum field theory predicts that every field, the electromagnetic field, the electron field, the quark fields and so on, contributes zero-point energy. These contributions come from all the possible modes of vibration, from the longest wavelengths to the shortest. When you sum them up, even with conservative assumptions, the predicted energy density of empty space becomes unimaginably large. If you do the calculation all the way up to the Planck scale, the result is roughly 10 to the power of 120 times larger than what astronomers observe. That means theory predicts that the vacuum should be dense enough to crush the universe or cause it to explode in a fraction of a second. Instead, the universe expands slowly and gently with an extremely small but positive acceleration. This is the cosmological constant problem, also called the vacuum catastrophe. It is not a minor discrepancy. It is not a matter of tweaking a constant or adjusting a parameter. The predicted vacuum energy density from quantum field theory is so huge that if it were even remotely correct, galaxies, stars, planets, and life could not exist. Space-time itself would be violently unstable. Steven Weinberg, one of the fathers of the standard model of particle physics, spent decades thinking about the problem. In the 1980s, he showed that if the cosmological constant were even 100 times larger than its observed value, not 10 to the 120 times, just 100, galaxies would not form. The universe would expand too quickly for matter to collapse under gravity. Everything would be cold, thin, and structureless. The fact that our universe contains galaxies suggests the cosmological constant must lie in a very narrow window. Weinberg famously used this argument to propose an anthropic explanation. We observe the cosmological constant we do because only universes with values near zero allow observers to exist. It was a controversial idea, but one of the few that matched observations. But even if we accept that logic, it doesn't solve the core issue. Quantum field theory still predicts a vacuum energy density wildly larger than what we see. This is where the Casimir effect becomes important. It does not fix the problem, but it proves the starting point is real. Zero-point energy exists. Vacuum fluctuations are measurable. The vacuum is not empty. The Casimir effect confirms that quantum theories are not inventing phantom energies. The vacuum really does behave like a physical system with structure and a baseline energy. When you place boundaries in the vacuum, it responds. The force created by the Casimir effect is a direct probe of the vacuum's underlying activity. But the Casimir effect measures only energy differences, the change in vacuum energy between one configuration and another. It does not measure the absolute energy of the vacuum. This is crucial. In quantum field theory, absolute values often diverge, but differences are finite and measurable. The Casimir effect is a difference. It tells us nothing about the overall vacuum energy that curves space-time. It's similar to measuring the height of a hill by looking at the incline, without knowing the altitude above sea level. The Casimir effect measures the slope, not the absolute height. This is why the effect cannot solve the cosmological constant problem. It demonstrates that zero-point energy is real, but it does not tell us why the universe does not act as if it is filled with 10 to the 120 times more energy than we observe. Cosmologists have tried various approaches to fix the discrepancy. Some involve symmetry principles that cancel out contributions to vacuum energy. Others explore the possibility that gravity responds differently to vacuum energy than to ordinary energy. Some theories propose new fields that dynamically adjust the cosmological constant over time. Others suggest that quantum gravity, the as-yet unknown theory that unifies general relativity and quantum mechanics, will ultimately resolve the problem. As of today, none of these explanations are confirmed. The mystery remains. The dark energy that drives the universe's accelerated expansion appears extremely small compared to the predictions of quantum field theory, and yet it is not zero. That fact alone is remarkable. A perfectly zero cosmological constant would be simpler mathematically, easier to explain, and more aesthetically satisfying. Instead, the universe gives us a value that is tiny, positive, and deeply unnatural from the perspective of particle physics. We live in a universe where empty space has just enough energy to push galaxies apart over billions of years, but not enough to tear them apart instantly. How such a balance emerges remains one of the most profound open questions in science. The Casimir Effect sits at the heart of this puzzle. It confirms that the vacuum has structure, that quantum fields fluctuate, that zero-point energy is not an artifact of equations, but a physical reality. It tells us that the vacuum can exert forces, respond to boundaries, and influence matter. But it also reminds us that the vacuum's true energy, the energy that determines the fate of the cosmos, is still mostly hidden. The Casimir Effect is like tapping on the surface of a vast unknown ocean and hearing an echo. The echo is real. The surface is real, but the depth, the currents, and the pressure miles below remain concealed. Vacuum fluctuations shape the microscopic world. Dark energy shapes the universe on the largest scales. Between the two lies a gap of 120 orders of magnitude that no one has yet bridged. It is a reminder that our understanding of the universe is still incomplete, and that even the simplest question, what is the energy of empty space, remains one of the hardest questions science has ever faced. For most of human history, the idea of nothing seemed simple. If you remove the objects from a room, you're left with nothing. If you drain all the air from a chamber, you're left with nothing. If you imagine outer space, far from stars and planets, you picture a cold void, an expanse of nothing. But the Casimir Effect challenges that intuition at the most fundamental level. It says that even when you take everything away, all matter, all light, all particles, something remains, something active, something measurable. The vacuum, which was once thought to be a silent stage on which the universe performed, becomes a participant in the drama. The fact that empty space can exert pressure forces us to confront a difficult question. What does nothing actually mean? In everyday language, nothing is a negative definition, the absence of things. If your hand is empty, you are holding nothing. If a container is empty, it contains nothing. But physics cannot work with vague, negative definitions. It needs to describe what exists, what is measurable, and what influences behavior. When you look closely enough, the vacuum begins to reveal itself as something far more complex than a simple absence. Quantum mechanics and quantum field theory show that vacuum is not nothing. It is the lowest energy state of a collection of fields that permeate all of space. Those fields cannot sit perfectly still, even at absolute zero. The uncertainty principle prevents them from having exactly zero energy. They must fluctuate, ripple, and vibrate, however slightly. This jitter, subtle, unavoidable, and omnipresent, is the fabric of the quantum vacuum. So when we speak of empty space exerting a force, we are not attributing magical properties to nothingness. We are acknowledging that the vacuum is a physical environment with structure. The Casimir Effect is not a force from nothing. It is a force from the way quantum fields behave when constrained. It is a difference in vacuum energy created by geometry. Philosophically, this pushes us away from the classical idea of a void and toward a more nuanced understanding of emptiness. In classical physics, emptiness was an inert background. It did not influence matter or energy. It simply existed as the absence of things. But in modern physics, emptiness has rules. It has dynamics. It plays a role. This is why many physicists prefer to avoid calling the vacuum nothing. It is misleading. If you remove every atom from a region of space, the underlying fields remain, they cannot be eliminated. They are woven into the structure of reality, as essential as space-time itself. This distinction becomes even more interesting when compared with philosophical or metaphysical ideas of nothingness. In philosophy, true nothingness, absolute non-existence, has no properties, no potential, no activity. It is the complete absence of being. It is not a medium, not a space, not a vacuum. It is literally nothing. But physics cannot access that kind of nothingness. Even the most perfect vacuum we can create in a laboratory is still filled with quantum fields. Even intergalactic space contains fluctuations. Even the vacuum inside a Casimir cavity has energy. Physics has never observed, and likely cannot observe, a state with no fields, no fluctuations, no laws, and no structure. This highlights a subtle but important point. When physicists speak of the vacuum, they are not speaking of metaphysical non-existence. They are describing the lowest energy configuration of the physical universe. It is as real as a magnetic field or a gravitational field. Vacuum energy can bend space-time. Fluctuations can produce observable forces. The vacuum is not the absence of physical law, it is a consequence of physical law. The philosophical tension appears because the word nothing has different meanings in science and philosophy. In everyday speech, nothing means an empty container. In philosophy, nothing means the absence of all existence. In physics, nothing means the ground state of fields. These three meanings are not interchangeable. When we say empty space exerts pressure, we are using the physical definition, not the philosophical one. We are not saying that literal non-existence is doing something. We are saying that the vacuum, a complex, field-filled, rule-bound environment, has internal dynamics. The more we learn about the vacuum, the harder it becomes to think of it as a background stage. It behaves more like a character in the play. It influences the motion of particles. It shapes the behavior of atoms. It even contributes to the expansion of the universe itself. And it is always active. In classical physics, motion stops at absolute zero, energy dissipates, atoms freeze in place, perfect stillness becomes possible. But quantum mechanics refuses to allow perfect stillness. Even at absolute zero, fields must fluctuate. They cannot collapse into zero energy. The uncertainty principle forbids it. This creates a universe that is fundamentally restless. There is always some level of jitter, some whisper of fluctuations, some hint of structure. The vacuum never sleeps. It never relaxes. It never reaches a state of perfect calm. Every inch of space is alive with tiny temporary events. Births and deaths of virtual excitations, shifts in energy, momentary disturbances that pass too quickly to observe directly but influence everything nonetheless. This idea is deeply counterintuitive. Our senses evolved to navigate a world where friction, pressure, and motion dominate. At that scale, it feels natural to imagine stillness. A rock can sit unmoving on the ground for centuries. A room can feel silent and empty. A container can feel like it contains nothing. But the quantum world operates on principles that defy classical intuition. Stillness is never perfect. Emptiness is never complete. The vacuum is an environment, not an absence. This leads to a deeper philosophical implication. If the vacuum is the ground state of the universe, then the universe has no true zero. There is no baseline of absolute nothingness. Everything we observe arises from a background that is itself full of activity. Some physicists and philosophers argue that this challenges the common question, why is there something rather than nothing? From the viewpoint of quantum field theory, nothing, in the philosophical sense, might be impossible within our current understanding of physics. The universe may not allow a state with no fields and no laws. The vacuum is not a blank slate. It is the lowest energy manifestation of the laws of nature. If those laws exist, then the vacuum must exist. And if the vacuum exists, something exists. This doesn't answer the metaphysical question fully, but it reframes it. Instead of asking why the universe contains matter, we might ask why the laws of physics exist. At all vacuum energy becomes a clue, not a conclusion. Another implication is that the universe is not divided into something and nothing as neatly as classical thinking suggests. The boundary between matter and vacuum is thinner than we imagine. Particles emerge from fields. Fields emerge from deeper principles. And the vacuum, the state we once considered empty, is part of the same continuum. Even the idea of space as a passive stage begins to collapse. In general relativity, space and time form a dynamic fabric that bends and curves. In quantum field theory, that fabric is filled with fields. These ideas merge into a picture where the universe is not built on top of a background. The universe is the background. There is no underlying emptiness beneath the fields. The fields are the foundation. When you look at the vacuum this way, the Casimir effect becomes a philosophical statement as much as a physical one. It says that the universe, even at its quietest, is full of potential. It says that boundaries shape emptiness. It says that reality is active at its roots. Even in a perfect vacuum, even at absolute zero, the universe vibrates. This constant, irreducible motion is not noise or chaos. It is structure. It is the sign that the universe is awake at every scale, and it reminds us that our classical intuition of stillness, emptiness, and silence is only an illusion created by our size and our senses. The Casimir effect is not just a tiny force. It is a reminder that the universe is never truly empty and never truly quiet. It is a glimpse into the deep architecture of reality, the architecture that remains even when everything else is stripped away. The vacuum is not nothing. It is the foundation on which everything rests, and it is always, always moving. Even though the Casimir effect is now a well-established part of quantum physics, the story is still unfolding. What began as a theoretical curiosity in 1948 has grown into an active field of research, with scientists pushing into new regimes, refining measurements, and discovering ways to manipulate vacuum forces in ways Casimir never imagined. The first generation of experiments focused on detecting the force at all, proving it existed, eliminating competing explanations, and confirming the predictions of quantum field theory. But once the effect became measurable and reproducible, the next phase of exploration naturally emerged: precision. How precisely can we measure the Casimir force? How accurately can theory and experiment be matched? And what new physics might be hiding in the tiny gap between them? Today's experiments use techniques far beyond what was possible in the 1990s. Atomic force microscopes, instruments capable of detecting forces 1,000 times smaller than what Lamoreaux measured, have become standard tools in Casimir research. Microfabricated torsion oscillators, high vacuum chambers, cryogenic setups, and materials engineered at the atomic scale all allow physicists to probe the Casimir effect across a wide range of distances, geometries, and temperatures. These modern measurements explore not just the strength of the force, but also how it behaves under different conditions. For example, the force changes depending on whether the plates are metals, dielectrics, semiconductors, or even exotic materials like graphene. It changes if surfaces are patterned or textured. It changes with temperature. It changes depending on the shape of the objects, whether they are flat, spherical, corrugated, or layered. One of the most important developments of the past 20 years has been the exploration of Casimir forces between non-planar surfaces. Casimir originally calculated the force between two infinite parallel plates, but in reality, surfaces come in all shapes. Physicists have now measured the effect between spheres and plates, cylinders and plates, and even between objects with engineered shapes designed to amplify or suppress certain vacuum modes. These geometric variations are not just mathematical games, they reveal how boundary conditions sculpt the vacuum, channeling fluctuations in ways that can increase or decrease forces. Materials science has also become central. The Casimir force depends on how electromagnetic fields interact with surfaces, which means the properties of those surfaces matter. Researchers now use gold, aluminum, silicon, graphene, metamaterials, and even superconductors to test how different electromagnetic responses influence vacuum fluctuations. In superconductors, for example, the way electrons pair up changes how they reflect electromagnetic modes. Theoretical predictions suggest that the Casimir force might behave differently across the superconducting transition, an idea still under investigation. Experiments are also exploring the effect in liquids rather than vacuum. By immersing surfaces in carefully chosen fluids, the relative dielectric properties of the materials and the liquid can flip the sign of the force. Under the right combination of materials, the Casimir force can become repulsive rather than attractive. This opens up new possibilities, especially in nanotechnology, where repulsive forces could help prevent stiction or enable frictionless microdevices. But perhaps the most dramatic extension of Casimir's idea comes from the dynamical Casimir effect, a phenomenon predicted decades ago but only observed in 2011. The original Casimir effect emerges from static boundaries, objects that sit still and shape the vacuum. The dynamical Casimir effect arises when boundaries move. If you accelerate a mirror quickly enough, extremely quickly, the motion disturbs the vacuum in such a way that real photons can be produced. Vacuum fluctuations are amplified by the moving boundary, turning virtual excitations into detectable light. In practice, no one can shake a physical mirror fast enough. The speeds required are near relativistic, oscillating billions of times per second. But superconducting circuits can simulate this motion. In 2011, a team of Swedish physicists used a superconducting quantum interference device, or SQUID, to create a boundary condition that changed extremely rapidly. Instead of physically moving a mirror, they changed the effective length of an electronic cavity at high frequencies. This produced microwave photons from the vacuum, real particles created from quantum fluctuations. It was a remarkable demonstration, energy extracted from vacuum fluctuations by changing the geometry in time instead of space. It confirmed yet another subtle prediction of quantum field theory and opened new doors for research into quantum information, photon generation, and vacuum engineering. These modern experiments hint at a future where vacuum forces might become tools rather than obstacles. In nanotechnology, engineers already account for Casimir forces when designing tiny machines, but as our ability to manipulate materials, shapes, and electromagnetic properties improves, there may come a time when we can deliberately tune vacuum forces to perform useful functions. Imagine nanoscale actuators powered not by electrical currents, but by carefully shaped boundaries that harness vacuum pressure. Imagine frictionless bearings, where Casimir repulsion keeps surfaces from touching. Imagine devices where motion is controlled not by conventional forces, but by engineering the vacuum landscape itself. None of these ideas violate physics. They are not science fiction. They are extensions of what experiments already show, that the vacuum is sensitive to geometry, that its energy can be shifted, and that those shifts produce real forces. This does not mean we will ever build engines powered by zero-point energy or warp drives sustained by negative energy densities. Quantum inequalities, thermodynamic constraints, and the inherent weakness of the Casimir force limit what is possible. But within the domain of nanotechnology, where distances are tiny and forces small, vacuum engineering may become a practical tool. The future of Casimir research is likely to follow several parallel paths. One path is precision, improving measurements to test the limits of quantum field theory. Any deviation between theory and experiment could signal new physics. Some researchers hope that Casimir experiments might reveal hints of extra dimensions, modified gravity at small scales, or new particles that alter the behavior of vacuum fluctuations. These possibilities are speculative, but precision experiments at the quantum frontier sometimes uncover surprises. Another path is materials innovation, exploring how the Casimir force behaves with graphene, topological insulators, metamaterials, and other exotic surfaces. Some theoretical studies predict that materials with unusual electromagnetic responses could reshape vacuum fluctuations in ways completely different from ordinary metals. These materials might someday allow engineers to craft vacuum forces with custom magnitudes or signs. A third path is dynamic vacuum control, inspired by the dynamical Casimir effect. As circuits and cavities become more advanced, physicists may learn to manipulate vacuum fluctuations in time as well as space. This could lead to photon generation techniques, quantum amplifiers, and new methods for controlling quantum states. A fourth path is applied nanotechnology, where vacuum forces will play a role in sensors, switches, resonators, and tiny machines. Instead of treating the Casimir effect as a nuisance, future devices may harness it deliberately, using patterned surfaces or tuned materials to guide motion with quantum pressure. At the heart of all these possibilities is a shift in mindset. The vacuum is no longer a passive environment. It is a medium with structure, energy, and behavior. It can be shaped, probed, and controlled within limits. It is not a blank backdrop, but an active participant in physical processes. As physicists continue to explore these frontiers, the Casimir effect remains both a guide and a reminder. A guide because it shows how the vacuum responds to boundaries and geometry, a reminder because it reveals that the universe contains layers of subtlety that classical thinking never imagined, even at absolute zero, even when nothing seems to be happening, even when matter and radiation are stripped away. The vacuum remains alive with fluctuations. The universe is never still. What began with two metal plates in a theoretical calculation has grown into a window through which we glimpse the restless nature of reality. Every experiment, whether measuring a tiny attraction, generating photons from moving boundaries, or exploring new materials, reinforces the same insight. Emptiness is not empty. It is structured. It is active. It is fundamental. And as our tools improve, as our questions evolve, and as our technologies shrink into regimes where quantum forces dominate, the vacuum will continue to reveal its character, not as a void, but as a dynamic field that underlies everything. The future beyond the Casimir effect is not about exploiting nothingness. It is about understanding the deepest something that hides beneath our concept of empty space, and learning, one experiment at a time, how the quiet background of the universe shapes the world in ways we are only beginning to grasp.